Ngalakin kadijan nyunga boja.
No, we get the formula sheets. So you already know what you're getting. You need to start but I think the formula sheet gives you all the yeah. All this yeah. So it was okay. So far the understanding is going all right.
All right, it's 3 o'clock, so we can start. We've talked about economic dispatch in the last lecture. We've got through a fair amount of the chapter, this section in the last lecture. We have a little bit more to go with regard to economic dispatch. So economic dispatch is about, well, we have a number of generators that can generate electricity, right? And there is a load demand. So how do we allocate generation for different generators in the most cost-effective way to satisfy the demand is economic dispatch. Yeah, because some generators are more expensive to generate electricity, some generators are less expensive. And it can also be a function of the power it generates. So as long as we know the cost of generation as a function of the power for that generator, so when the power requirement for the generator increases, the cost can increase. As long as we know that function, we can perform an optimization to minimize the overall cost of meeting a particular demand. So how do we allocate power to different generators, assuming no assuming transmission loss zero, neglecting them? If we look at the incremental cost of generating electricity, incremental cost per megawatt unit of power, so incremental cost per megawatt, for example, incremental cost per unit of power for a particular generator, when that incremental cost per unit of power is the same for all the generators, that's when we have the optimum solution, the least cost of generating the electricity. So what we essentially then want to do is, if we have the cost function for each of the generators, cost of generating, we find the incremental cost for each of the generators, right? Incremental cost per unit of power for each generator. We equate them, right? We equate them, and that is the solution. When we equate them, we will have solution for G, we will have a solution for C1, C2, C3, etc. We will have a solution. We will have a solution. We will know what is PG1, what is PG2, what is PG3, etc. So that's the power that we need to assign for each of those generators to minimize the overall cost. And also notice that when the incremental cost for each of the generators, when we equate them, they also equal, we say that equals to a particular value, or we denote that incremental cost to be lambda. We just say, well, that's the lambda value, right? So we determine the lambda value by equating the incremental cost per unit of power for each of the generators. So if we then know, let's say there's two generators that need to supply the entire load, so we know C1 and C2. So we differentiate C1 with respect to P1, we generate C2 with respect to P2, and we equate them. And when we equate them, we can, and also we have another, when we equate them, we have one equation. We also have another equation that says P1 plus P2 must equal the load, right? So we have another equation, second equation. So those two equations are linear. Well, with two equations and two unknowns, we can solve for the unknowns, P1 and P2. So that solution for P1 and P2 is the dispatch, is how much we're going to assign each of those generators to generate. And that will be the least cost of meeting the demand using the two generators. So we've talked about that. So that equating the incremental cost per unit of power to optimize the cost of generation is for the case when the transmission losses are ignored, right? So today, now we're going to look at how do we tackle if we have to take into account the transmission losses as well, because the generators not only have to generate what is required by the load, it also needs to generate the losses in the transmission line. Yeah, losses in the transmission line. So previously we ignored the transmission line losses. Now we're not going to ignore the transmission line losses. So what is the optimum solution if we are not going to ignore the transmission losses? What is the optimum solution? Well, think about it like this. Let's say you have two generators, G1 and G2, and let's say your load is closer to generator 2, right? So generator 1 is a little bit far away. So then perhaps it makes more sense for generator 2 to supply more power, because if generator 2 supplies more power, the losses will be minimal because load is closer to generator 2. Yeah? So if we are going to account for transmission losses, we're going to have a different solution, and the solution is going, I will directly go to the solution. The solution is going to be like this. The solution is going to be, see, previously what we did, we took the incremental cost, right? Incremental cost of generating a unit of power for each generator. We equate those things. Now we actually multiply that incremental cost by a penalty factor. For each of the generators, we actually determine a penalty factor, right? We multiply by the penalty factor. So incremental costs multiplied by the penalty factor for a generator. So for all the generators, we have an incremental cost and multiply those by the relevant penalty factors, and we equate them all, and that's the optimum solution. And that's the lambda value, right? We say all that is equal to lambda as well, if you like. Yeah. So what is the penalty factor? Well, penalty factor you can see here. 1 over 1 minus partial derivative of the losses with respect to that generator, PGI. So PGI can be PG1, PG2, etc. So we are PL is the transmission loss, yeah, because transmission loss can be a function of all the power that is generated by the different generating sources. Yeah. So when we see an example, it will make more sense. But what you need to remember is, for each of the generator, we need to compute not only the incremental cost, but that penalty factor Li, which we need to multiply, and then we equate the multiplication of the penalty factor with the incremental cost for each of the generators. We equate, and that's the lambda value, and that's what's going to give us the optimum solution. All right. So let's look at an example here. The cost of for generator 1 is a function of the power it's going to produce, right? The cost of generating electricity using generator 2 is a function of the power that it will produce. That makes sense. So obviously for generator 1 and generator 2, when it generates more power, the cost of generating a unit of power increases. Yeah, that's what that says. Now the transmission loss is given by this expression, which is a function of P1. It's a function of P2 as well, P1 and P2. So the transmission loss is a function of P1 and P2. Yeah? So what do we have to do? We have to determine the incremental cost for C1. That's no problem. We differentiate C1 with respect to P1. We need to find the incremental cost of generating for the generator C2. We differentiate C2 with respect to P2. That's not a problem. For each of the generators, we need to find a penalty factor. To find the penalty factor, we need to differentiate penalty factor for generator 1. We need to differentiate PL with respect to P1. Right? For generator 2, to determine the penalty factor, we need to differentiate PL with respect to P2. Right? So when we differentiate with respect to P1, right, to determine the penalty factor for generator 1, so we have this, right? We have that partial derivative, and we can substitute that in there, and we'll determine the penalty factor for generator 1. And if we differentiate PL with respect to P2, we have that partial derivative there, which I highlighted in green. We can then determine L2, right? Penalty factor relevant to generator 2. And then the penalty factor multiplied by incremental costs for each of the generators, we equate them. That's the solution we are after. And that's the optimum solution, taking into account the transmission losses. Okay, so it can be done. So this is an example, right? So C1 is given, C2 is given, P1 and P2 has some limits, right? Of course, if it's inside the limits, then, you know, if it's outside the limit, then it will saturate, and it'll no longer, incremental cost will no longer be determined by that, will be determined by the other generator, right? And here we are told that lambda for this particular case is actually $16 per megawatt hour. We've been told the lambda value. So then we need to determine the power output for each of the units. So it's straightforward. We compute, this is the penalty factor, incremental cost for generator 1, penalty factor, incremental cost for generator 2. We're given the lambda value is 16. Penalty factor for generator 1 can be determined by differentiating PL with respect to P1. We obtain that expression. Same way we can obtain the penalty factor L2, right? So incremental costs can be obtained by differentiating the respective cost functions, right? And then we can then multiply L1 by that, L2 by that, equate them, right? Equate them like in here, and then we can determine P1 and P2, right? You just solve the equations, P1 and P2, and then the corresponding transmission line loss, we substitute P1 and P2 in the equation and we can find out, or we can calculate, compute the loss is that. So the demand for power demand, which is the load, is what the generators produce minus the loss. So that's the load. And of course, to supply the load, there is an associated transmission loss, which is that amount there. So what is the cost? Because we know the optimum P1 and P2, then we can determine C1 and C2, right? By substituting P1 and P2 in the cost functions, right? That's C1 and that's C2, and it will give us this value. The cost is $8,357 per hour to supply that load at that given time, right? So, so that is economic dispatch. I think you know, right? If ignoring transmission losses, we don't need a penalty factor. If you want to not ignore the transmission losses, we have to associate a penalty factor with the incremental costs. Right. So economic dispatch. Yeah.
It's just I was thinking about economic dispatch in terms of also the renewable energy for that, and we were just analyzing it in terms of fossil fuels.
So say it again. Your question is?
I was just wondering how economic dispatch would work with introduction of renewable.
Right. So the question is, how would economic dispatch work with renewable energy? That's the question. Now, see, to be able to dispatch, renewable energy sources are not a dispatchable source because the generation is intermittent. So we cannot say this particular generator will generate a certain amount of prescribed power. So it's not a dispatchable source. So renewable energy can only be a dispatchable source if it's linked with a battery. If it's associated, if it's combined with a battery, so that when there is excess energy, it's stored, and when the source is producing less than the requirement, the battery kicks in and provides the difference. Because dispatchable means what is requested, what is allocated for a particular generator, it needs to supply. It needs to supply. So in economic dispatch, not all the generation sources are actually, as I said, doesn't cost the same. Like for example, some coal power plants can be cheaper to produce electricity. Nuclear power plants can be cheaper because the fuel is cheaper, nuclear fuel is cheaper. So then those will not be part of the economic dispatch algorithm. Those generators will supply a base load, right? Like a base load. So the economic dispatch will be for the power over and above the base load. Yeah, for generating power over and above the base load. Yeah, so there will be base power stations, and there will be other power stations that will participate in economic dispatch, right? So the economic dispatch criterion has been derived for power system area consisting of fossil fuel generating units. That's what we've done, because with fossil fuel generating sources, you can control the generation. You can determine how much you can allocate a particular, a specific generation amount for a fossil fuel source. In practice, however, an area has a mix of different types of units, including fossil fuel, nuclear, pumped hydro, pumped storage hydro, wind, and other types. So we have different types of generation sources. So nuclear, although the fixed cost for a nuclear unit may be high, their operating costs are low due to inexpensive nuclear fuel. As such, nuclear units are normally base loaded, so they are used as a base power station to provide the base load at rated outputs. So it will operate at the rated output because you want to just utilize that to its maximum. That is, the reference power settings of turbine governors for nuclear units are held at constant at rated power output. Therefore, these units do not participate in load frequency control or economic dispatch. To participate in load frequency control, it needs to adjust the power output, because when the demand is low, generation needs to be reduced. When the demand is high, generation needs to be increased. Because if you don't adjust the generation based on the load, then the frequency can change. Yeah, because if there is more generation than the demand, you have the generation sources will start to accelerate, and frequency will go up. And the opposite happens if the load is high, the generation is low. If the load is high, generation is low, starts decelerating. Yeah, the synchronous machines speeds will decelerate, rotor speeds. So pumped storage hydro is a form of energy storage, right? Pump hydro is a form of energy storage. So it's like a battery. What you do is during off-peak time, when the electricity price is cheap, you actually utilize the machines as motors, and you pump the water into an elevated storage, into a storage area. And when the electricity cost is high, you utilize the stored water, you utilize the potential energy, you convert it back into kinetic energy and electricity, and generate, you generate electricity by converting kinetic energy into electrical energy. So it's a form of storage. When the electricity price is cheap, you actually pump it to a higher elevated position, elevated storage, and then you utilize it when the cost is, during peak hours, when the cost of electricity is high. During off peaks, these units are operated as synchronous motors to pump water to higher elevation. Then during peak load hours, the water is released and the units are operated as synchronous generators to supply power. As such, pump storage hydro units are used for light load buildup and peak load shaving. So if you want, if there is a peak load and you want to shave that peak or provide the energy for that peak, we can use, pumped storage hydro to do that. Economic operation of the area is improved by pumping during off-peak hours when the area lambda is low. So when you're talking about area is it's a particular geographical area, because you want to ensure that the generation sources can meet the demand in that particular geographical area. Yeah, so that's when you're talking about electrical area is a defined boundary. Yeah, defined boundary in a particular in a specific geographical area. So economic operation of the area is improved by pumping during off-peak hours when the area lambda is low, because lambda is the incremental cost of generating electricity per unit of power, right? So lambda tells if the incremental cost of generating electricity per unit of power. So when the area lambda is low, in other words, the cost of electricity is low, you use the synchronous machines as motors, as stated before, and when area lambda is high, you use the synchronous machines as generators and utilizing the stored potential energy in the water to generate electricity. Hydro. In an area consisting of hydro plants located along a river, The objective is to maximize the energy generated over yearly water cycle rather than to minimize total operating costs. Because if you, as a private company, has built a power plant near a river, I mean, your objective is to using the water to actually provide the generate the maximum amount of power. That's the objective, right? That's what that sentence is telling. Not necessarily not necessarily minimizing the total operating cost. You just want to generate as much as possible, because when a company, when you generate as much as possible, that particular company will then profit more because it's generating more units of energy. Reservoirs are used to store water during high water or light loaded periods. Although some waterways, water may have to be released through spillways. Also, there are constraints on water levels due to river transportation, irrigation, or fishing requirements. So some environmental requirements that needs to be taken care when generating electricity using hydro. Optimal strategies are available for coordinating outputs of plants along a river. Economic dispatch strategies for mixed fossil fuel hydro systems are also available. With hydro, sometimes you need to take care of the environment. You need to make sure that there is adequate water flowing in a river for transportation, because there will be boats and other activities on a river. So and also you want to minimize the impact on the plants in the river, the fish, and so on. Techniques are also available for including reactive power flows in the economic dispatch formulation, because we have active power balance, we also need to balance reactive power. So economic dispatch are also available for reactive power balance, or meeting the reactive power requirements, because we only talked about the active power power requirements, whereby both active power and reactive power are selected to minimize the total operating costs instead of just the active power alone. In particular, reactive power injections from generators, switch capacitor banks, and static VAS systems along with transformer step settings can be selected to minimize the transmission line losses. Now, with regard to meeting the reactive power requirements, generally we don't like generate reactive power at a generating source, because reactive power can be generated using things like capacitor banks and STATCOMs and so on. So usually in economic dispatch, we only care about the active power. Reactive power is generated at the point of consumption, can be generated at the point of consumption, because you can also minimize the losses, because you're not transporting that reactive power over the line. However, electricity companies usually control reactive power locally, as I said. That is, the reactive power output of each generator is selected to control the generator terminal voltage, and the reactive power output of each capacitor bank or static VAS system located at the power system bus is selected to control the voltage magnitude at the bus. So in this way, reactive power flows on transmission lines are low, and the need for central dispatch of reactive power is eliminated. So how do we adjust the reactive power? Because the reactive power has an impact on bus voltage. So when the bus voltage changes, when it increases, then we either supply or we adjust the reactive power. Same, if the bus voltage decreases, we again adjust the reactive power supplied by a capacitor bank connected to that particular bus locally. So that's all about economic dispatch. So our focus on economic dispatch was to dispatch the active power that is required to balance the supply and demand, right? Right, so that brings us now to the section on transient stability. Transient stability. So transient stability talks about, well, imagine a power system in steady state. In other words, you have a bunch of generators, they are supplying a particular load, and then they can be in steady state. If the load doesn't change, generation amounts don't change, they are in steady state. All of a sudden, imagine the load changes. So when load changes, the generation has to be adjusted to meet the demand. So then the steady state operating point will move from the original steady operating point, steady state, to a different steady state. So the time in between those two operating points is the transient period. So it's a transient behavior that we're going to study, transient stability in particular. Does it go to a stable operating point? Like you have one operating point, when load changes, the generation has to be adjusted. Does it move to another stable operating point? Or is there causes for instability when load changes? That's what we're going to look at in this section. So just some time scales. Lightning propagation, we are looking at 10 to the minus 5 seconds time scale. Switching surges, inverter-based control, like in the millisecond range. Stator transient and synchronous resonance, 0.1 of a second. Transient stability, something like 0.1 of a second to about 10 seconds. So when loads change, if the system is stable, then it will move from one operating point to another stable operating point within about 0.1 to 10 seconds. That's the time scale we are looking at. And then if you're talking about governor and load frequency control, you're talking about 10 seconds to hundreds of seconds, right? Boiler dynamics and voltage stability, again, about 1,000 seconds. Power unit commitment, 10 to the 5. Unit commitment is how often you tell which generator is producing how much energy. Yeah, because you got to tell, you have various generators, economic dispatch, unit commitment. Economic dispatch and unit commitment, you commit a particular unit. Yes, is linked to economic dispatch. You tell a particular generator, well, this is how much you need to supply. So these are the time scales for those different events. So figure shows US Eastern interconnected frequency variation after loss of 2600 megawatts of generation. So not only the loads can change, but the generation can change as well. All of a sudden we might lose some generators. So this is what has happened in the US after losing 2600 megawatts of generation. So you can see the generation has all of a sudden dropped, right? And consequently the frequency has dropped because machines are slowing down, because decelerating. Machines are decelerating because it can't keep up with the load. So figures show the frequency change as a result of sudden loss of a large amount of generation. Again, you can see in the US the frequency is 60 hertz, but in Australia it's 50 hertz, in the US 60. So with loss of generation, you can see the red curve there. The frequency has dropped from 60 to about 59.7 something. Sorry? Well, that's the standard they have chosen. It's a standard, right? So you could choose 50, you could choose 60, as long as it's consistent, reasonable. So 60 is what US have chosen. We have Australia, it's 50 hertz. So transient stability, power flow is used to determine the quasi-steady state operating condition for a power system. So we've studied power flow, right? So when you done a power flow, it's like you are determining the steady state operation. So once you've done that, when you find out all the voltages at different bus bars, well, that's the operating point, right, for a given load condition. Now, if the load condition then changes at a particular bus bar, you would need to, the voltage at bus bars will change. It will move to a different location, like as you see on the right? So, and in between, it will go through some of those operating, the voltages at various nodes on the network will go through a transient. It will change, like oscillate a little bit as shown there, and will reach a new operating point if the system is stable, right? And we will talk about stability. What are the ways we can do this? Dynamic simulation is used to determine whether following a contingency like a load change or generation loss, the power system returns to a steady state operating point. Goal is to solve a set of differential and algebraic equations. Because you have generators, those generators can be described by a set of differential equations. Then you have the voltages at various busbar nodes can be regarded as algebraic variables because they change quite fast relative to the variables in a generator. Variables in a generator, are linked to rotating components, which are mechanical components, which are slower. So those variables associated with the generators respond slower, so they can be regarded as dynamic variables. Those variables that changes quite fast can be regarded as algebraic variables because they change quite fast. So if we want to mathematically model an entire network, we will have differential and algebraic equations. That's what that is saying. Of course, if the system has reached steady state, then dx dt there would be 0, and fxu equal to 0, gxu equal to 0 is the load flow solution that we did previously, right? Now when the system changes, the network topology changes, or the load changes, or generation changes, then dx dt will no longer be 0 for at least for some time during the transient period, and those variables settle at a new place, a new operating point, right? Now, after a contingency, the operating point will reach a stable operating point, provided that system is stable, right? In order to operate as an interconnected system, right, and it to be stable, all generators and the synchronous machines must remain in synchronism with one another. They must be synchronized. It must remain in synchronism. Synchronism requires that for two-pole machines, the rotor turns at exactly the same speed. So the frequency of the generators have to be the same, 50 hertz, then it's 50 hertz, all the generators. But if something rotates at one speed and another one rotates at a different speed, then it can lose synchronism. Loss of synchronism results in condition in which no net power can be transferred between the machines. So if they are operating at different frequencies, we won't be able to transfer power, and the system will fail. A system is said to be transiently unstable if following a disturbance, one or more generators lose synchronism. So after an event, if one or more generators lose synchronism, in other words, either generator speeds up or decelerates and settles at a different speed, then we say it's transiently unstable. In order to study transient response of a power system, we need to develop models for generators which are valid during transient time frame of several seconds following a system disturbance. We need to develop both electrical and mechanical models for the generators. So the model for generator is something like this. Say the simplest generator model, known as the classical model, treats the generator as a voltage source behind some reactance. The voltage magnitude is fixed, right? Voltage magnitude is fixed, which is EA, but its angle changes according to the mechanical dynamics. So the magnitude of EA is fixed, the angle theta can change. On the right hand side, the terminal voltage is V2 angle 0, so that's the reference we are choosing, angle 0. And the generator is injecting current into the terminal, so that terminal can be regarded as a bus bar, if you like, right? And notice this is an important equation. Notice how much power is injected into the node. How much power the generator is producing, because there is no loss, because it's a reactance there, right? It's the same amount of power that is injected into the terminal. Now this is a key equation. Take a look at the angle at the terminal. The angle at the terminal is 0. Take a look at the angle of the internal of the generator is delta. This is a very important equation. And between the generator and the bus bar, there is only a reactance, right? So notice how much power is being injected. The amount of power that's being injected, this is a very important equation, is a function of delta. And delta is the angle difference between the source on the left and the terminal voltage, which is 0, right? So the power that is injected depends on the angle difference, delta. So, and also you take the magnitude of the two voltages, EA and VT, divided by the reactance that connects the 2 points on the left and the right, XD dash in this thing, multiplied by sine delta. That's an important equation. So we know how much power this generator can inject. Very important. Okay? Yeah? Is all good? Okay. Generator. Okay. So this is a generator mechanical model. So what do we have here? So on the left, we have some fuel, like we burn some coal. Then there's a boiler. So when you burn coal, it produces a lot of heat. And then that will boil some water, produce steam. And then this steam will pass through a valve into a turbine. And it will spin the turbine. And the turbine will output a mechanical torque. Right? Because turbine is rotating, it outputs a mechanical torque, which is connected to a generator. So if you have and you have a mechanical input into the generator will then produce electricity. So it will provide an electrical torque. Electrical torque and electrical power are linked, because torque times speed is power, isn't it? So if the speed in per unit is 1, torque is essentially like power. Torque times 1, because in per unit is 1. So torque is also equivalent to power. So here we have another important equation, which is called the swing equation. So alpha is the angular acceleration of the turbine, and also which is also the rotor. Right? Because the turbine is connected to the rotor. They're spinning at the same rate. So angular acceleration times inertia, right? It's like force times, the mass times acceleration. Inertia times the angular acceleration must equal the unbalanced force, unbalanced torque in this situation. Mechanical torque minus electrical torque minus some friction. So that's an important equation as well, and this is called the swing equation. Swing equation, because it talks about an angle, right? Angular acceleration of the rotor, right? Very important equation. So now that equation, if you look at it, right, it's also, okay, It's also similar to, let me move forward and come back again, to a spring mass system. Mass times acceleration on the right hand side, right? Mx double dot is mass times acceleration, right? Plus some friction coefficient times the velocity, right? Must equal the unbalanced force, which is the gravity minus the force on the spring. They are acting in opposite directions, so you have the negative sign. So it's like a spring mass system, right? Yeah, because that constant times the friction times the velocity dx dt, it should be on the left hand side because that's a force as well. Yeah, so you have Newton's law, mass times acceleration is the unbalanced force. So the swing equation that we are looking at is essentially like a spring mass system. Mass times acceleration is equal to the unbalanced torque minus the friction. What? Every 40, it was idle. Nobody's here watching, right? Yeah, in the lecture hall there are only people. Yeah. Right. Okay. I'll just keep it on just in case somebody turns up online. Yeah. Okay. So that's what we got. So here, so we can say that the mechanical torque must equal the inertia times angular acceleration plus I've taken the term electrical torque from the left hand side to the right hand side, right? And I've also taken the friction torque from left hand side to the right hand side. And then you can multiply everything left hand side and right hand side by omega s, synchronous speed, speed of the rotor, so that torque times speed it becomes power. So that's mechanical power. On the other side, yeah, we simply have multiplied by synchronous speed. So we have then mechanical power. PM is the mechanical power, is the inertia times angular acceleration times synchronous speed plus the electrical torque. Omega s times TE is the electrical torque, right? Synchronous speed times the torque. Electrical torque is electrical power, which is a function of delta, PE delta. Now I said PE delta is an important function. Remember, it has to do with the angle delta, and delta is the angle of the generator internal voltage. So we have that equation, and then initially we assume there is no damping, so we assume TD equal to 0 if you like. Then you have the difference in mechanical power and electrical power must equal inertia times angular acceleration times omega s. So we can say then theta m is the rotor angle, right? Rotor angle is theta m. It must equal the speed times t plus the initial angle, delta, right? Initial angle delta. So theta m as omega st plus that angle delta, rotor angle. So theta m is the rotor angle. So we have omega m, which is the derivative of the angle theta, must equal omega s plus d delta dt, right? Delta is actually the angle of the internal voltage of the generator, E delta, right? Remember E delta must equal the rotor speed, and angular acceleration is you need to differentiate it once more. Omega s is a constant, so that disappears, so it becomes d squared delta dt squared is the angular acceleration, right? Angular acceleration is that. So yeah, so we have the mechanical power, right, which is the mechanical power output from the turbine, minus the electrical power output, which is P delta, must equal J omega S. Omega S is the synchronous speed, multiplied by the second derivative of delta, second derivative of delta, which is the which is well, delta is the angle that is associated with the voltage E. It's also called torque angle. Converting to per unit system, you need to divide everything by the power base, SB. So if you divide by SB, then we divide top and bottom by the same number, 2 omega S on 2 omega S. So we don't change the equation, and we arrive at that, and we can then define H to be that constant. Then we can write this equation. So P, again, that's the swing equation, mechanical power minus the electrical power must equal some H, some constant, second derivative of delta times 2 times omega S is the equation we are looking at. I think there is some mistake here. This thing here should be at, I think it should be, omega S should be here. Omega S is 2 pi f, then, right? Then we arrive at H on pi fs. 2 pi fs, right? Omega is 2 pi fs.
It's a sign in the formula.
Sorry?
It's a sign in the formula.
So I think, yeah.
But in the lecture slide, I have what you said. So
Which one? The corrected one?
H over
So I think the formula sheet needs to be corrected. Yeah, that is correct. What's on the lecture slide is correct. I have to correct the formula sheet.
So that means you go to the lecture slide.
Yeah, I may be having old version, but yeah. So there is some mistake there, right? So formula sheet needs to be corrected. So there, I think we have already printed the formula sheet, so there may be an announcement, but you can correct. But anyway, it does. Okay. So I already said that the swing equation can be linked to the spring mass system, right? It has the equation, sigma equation has the same form as the model for a spring mass system. So we want to now look at the transient stability of single machine infinite bus, SMIB, right? Single machine infinite bus. We want to look at the transient stability of this. To understand the transient stability problem, we'll first consider the case of a single generator connected to a power system bus with a fixed voltage, magnitude, and angle. So on the right-hand side, it's a node in a power network. An infinite bus has magnitude 1 and angle 0. Okay, it's a node on the power network, and on the left you have the machine, electrical machine, a synchronous machine connected to that. So there is some line impedance XL, JXL, right? And the model for the generator, you have EA delta JXD dash, right? Yeah. So this node here, that's a bus. That's a bus. Yeah, that's a bus on the electrical network. Yeah, so if you remember that that you have a generator, right, connected to a bus like that. Yeah. Okay, why is it called an infinite bus? What is an infinite bus? Infinite bus, the voltage does not change there. It doesn't matter how much current you're injecting. It's something large enough that you can't change its value. So the voltage there is always going to be 1 angle 0. And you can't change the angle either. Yeah? Yeah, swing bus is also regarded as a swing bus or slack bus, right? Is a, yeah, it'll have angle 0. We're going to choose that as our reference. Yeah, yeah, that's choosing as a reference. But here we can change the voltage magnitude at the terminal of the bus. It's all fixed. It's fixed. Doesn't matter what happens here to the left. On the right is fixed. Is a swing. Is an infinite bus. Right. Okay. So here comes that important equation, right? Oops. This important equation. Do you remember that? Because the power that is injected by the generator, because the generator and the infinite bus is connected. This reactance in between that, remember? So it's EA EA is the magnitude of the voltage of the generator multiplied by V bus. V bus would be magnitude of V bus is 1 divided by the reactance values, right? And sine delta, where delta is the angle of the generator voltage. Angle of the generator voltage. Yeah. So then we have this swing equation, right? Some constant times the second derivative of delta, right? That's our swing equation. Some constant times second derivative of delta plus some constant times the first derivative of delta must equal mechanical power minus the electrical power, right? Mechanical power minus the electrical power. There you go. That's the equation. So this is the electrical power. And that's the mechanical power. Yeah? Okay, now this is important. Now if you got this, so you know what this delta is, you know what that is, right? This is the electrical power, this is the mechanical power. So we are now going to do an example which is important based on that equation that we saw. Utilizing this equation that we saw, this is important now, right? So take particular care. Take particular care. Based on this equation, right? Based on this equation that we see here, we're going to do an example. Because we're going to analyze the transient stability looking at this equation. Because when there is a sudden event, what can happen? If a sudden event means we can have the electrical power requirement can drop. For example, let's say the bus all of a sudden becomes a short circuit. Terminal of the generator becomes a short circuit. Let's say for example, let's say this thing for some reason, right? This becomes a short circuit, right? If it becomes a short circuit, this voltage here will go from 1.0 to 0 volts, right? So that can happen, yeah? So we want to utilize this equation to study the transient stability, Because the generator is connected, then something might happen to the generator. Because, yeah, something might happen because the electrical power has already dropped to 0 because you're multiplying EA by V bus equal to 0, right? So electrical power has already gone to 0. Mechanical power may not already be there. Let's say you're providing a constant amount of mechanical power, yeah? And the electrical power is given by that expression, and because V bus is 0, because that bus happened to short circuit, the electrical power has already dropped to 0. Then we know that delta is going to change, right? Yeah, and delta is also linked to the rotor angle, yeah? So something's going to happen. So let's take a look at it, and we're going to do that by looking at this example. Single machine infinite bus example. Figure below shows a single line diagram of a 3-phase 60 Hz synchronous generator connected through a transformer, a parallel transmission lines to an infinite bus on the right. Yeah, that's the infinite bus. All reactances are given in per unit on a common system base. Infinite bus receives 1 per unit real power. 1 per unit real power at 0.95 power factor lagging, right? Okay. So P is equal to 1 per unit, 0.95 power factor lagging. And the infinite bus is receiving that. So if so infinite bus is that, right? Its voltage is 1 there, okay? So what is power? Power is V times I, right, times cos theta. Yeah, is equal 1, and it's a lagging power factor. In other words, V is 1, so I'll put 1 there, and if I can calculate the current, because I know the power factor is cos theta is 0.95, I can calculate the current, and the angle of the current has to be negative, right, because it's a lagging power factor. Current lags the voltage, so I can determine the current based on that statement. The internal voltage of the generator, so we need to determine the internal voltage of the generator. So we know how much current is flowing into the infinite bus, I know, right? How much current is flowing into the infinite bus, I know. You need to know the internal voltage of the generator. So how do we do this? All right, so this is what we have. We have EA delta on the left, that's the internal voltage of the generator. We have all the reactances, reactance of the generator, reactance of the line, transformer, reactances of the lines connecting bus 1 and bus 2, and the infinite bus on the right. Yeah? So, the two lines connecting 1 and 2, we can simplify because they are in parallel. Right? So, we can simplify, and then everything else, all the reactances are connected in series. Right? So all this can be one reactance value because these two guys are in parallel in series with that. Okay, one reactance value. Okay, so you have a generator on the left, you have a reactance in the middle, and you have an infinite bus on the right. That's what we got. Okay, that's what we got. So, and the reactance in the middle is this guy here. Just simplify, right? Parallel reactances, you can find what the equivalent reactance and you sum the series connected reactances. So, and you know the current that is flowing, right? We have determined the current that is flowing because you know the power, you know the voltage, you know the power, so you can calculate the magnitude of the current. You know the power factor is a lagging power factor, so you know the angle of the current is a negative value, so you know the current. Right? So you know the current, you know this reactance, you know the voltage on the right hand side, therefore you can figure out this. Right? Because E lambda must equal the voltage drop across the reactance plus 1 angle 0. So EA angle delta can be determined. This can be determined. So that, see here is the calculation of the current. Because you know power, you know that, bus voltage, power factor, and the angle is negative. We know the current, and here we calculate the EA. So EA has this value, has a magnitude and angle, right? So from that, the electrical power, we can determine the electrical power. Electrical power has to do with the magnitude of VA, bus voltage, which is 1, reactance, equivalent reactance connecting the two, the generator and the bus is, we know. So that's the electrical power, which is a function of delta. Yeah, which is a function of delta. Okay, so this is it, right? Okay. Now, the active power is 1 per unit. Active power is 1 per unit, right? Active power is 1 per unit. So that 1 per unit of power, electrical power, has to come from somewhere, right? Where is it coming from? The mechanical power. The mechanical power has to be that as well, right? I mean, energy is conserved. That active power of 1 per unit that the generator is providing is coming from the turbine, mechanical power. Yeah? Otherwise, how are we generating this electrical power? So, the mechanical power is 1. This is 1. Constant. 1. Right? And the electrical power has this curve, isn't it? P max, we've determined the value of P max, we have sine delta, right? So what does that mean? Electrical, in steady state, delta doesn't change, all the derivative terms are 0, right, on the left hand side. So electrical power and mechanical power must be the same, right? So it must be operating at this intersection point. It has to be operating either here or it must be operating there. Yeah? It has to be operating at one of those points. In fact, you will see very soon the stable operating point is this one. This is not a stable operating point. You will see why. I'll explain why. Right? So where the stable operating point is delta, right, on the left, and that's where it is operating. Okay? And I'll explain why this is stable. Assume that the rotor angle increase a bit, right? If the rotor angle increase a bit, what happens? It will move to this point, right? If delta increase a little bit, it will move to that point. And if the mechanical power is lower, electrical power is more, right? Yeah, in this situation. So what will happen? Pm minus Pe will be negative, right? And then what will happen? Delta will reduce because you have the second derivative of delta, a negative number, right? So delta will reduce. So when delta reduces, it goes back to that stable operating point, right? Let's see what happens here. See, you're here, right? Let's say you're at that point. See, here we were delta, we were a little bit right to the delta, but then it would drag it back, yeah? We'll drag it back to the operating point based on our differential equation, this thing here, yeah? Now, let's say you're here. If you're here, what does that tell you? Pm is bigger than Pe, right? Mechanical power is the constant horizontal line, is bigger than Pe. So Pm minus Pe is a positive number. So the right hand side is positive now. This is positive, right? So what will delta be? delta will increase, right? So a delta increases means it's going to go that way. So it is unstable. Yeah? Delta will increase. It won't pull it back to the operating point. Right? So whereas if you are here, your electrical power is bigger, this term here is bigger than that term, so this is negative. So the left hand side is a negative value, so delta will decrease.
And if you're just before the second delta, you'll pull it back all the way to the first delta.
Yeah, if you're here, let's see what happens here. If you're here, your electrical power is bigger than mechanical power. So this is negative, right? So then delta will start decreasing. So it will go all the way to that point.
But it is not electrical power.
Yeah.
It'll speed up at the top.
Huh?
It'll speed up at the top.
Yeah. It will come back. Delta will come back. See, delta comes back. Because if the electrical power is more than mechanical power, it starts decelerating. Isn't it? PM minus PE is negative. Yeah? PM minus PE is negative. So delta will start reducing. Delta is the angle of that E, internal voltage, and also delta is linked to the root angle, right? The speed or root angle omega m must equal omega t plus delta. Right? Okay. So, all right, so here, now this is interesting, right? Now take a look at this. So, initially, we have a particular load, right? We have a certain load, right? So the load is PMO, right? That's the mechanical power. PMO is the mechanical power. And it's supplying some electrical load. So the electrical power has to be the same as well. So, you know, that sine curve intersects PMO at delta naught. This is the electrical power. This is the mechanical power. Right? The left hand side intersections are the stable operating points. So electrical load is, let's say, PMO. So the mechanical power has to be PMO as well. Yeah? So initially, the turbine is providing a mechanical power output of PM0. Right? Generator is supplying a particular load, and that load is also PM0. So the angle delta is delta naught. Right? Angle of E has to be delta naught. Now, let's say all of a sudden, we increase the mechanical power, right? We increase the mechanical power. Then if you increase the mechanical power, then it increase the mechanical power to PM1, right? PM1. So what happens now? like PM1 because the load has increased, right? Load has increased to PM1 now. So we've increased the mechanical power to PM1. Right? So then the electrical power between delta naught and delta 1 is lower than mechanical power, right? So we start accelerating, so keeps moving up, right? And then it will keep increasing until delta 2, so that area A1 and A2 are equal, right? At delta 2, it will start coming back. So now we have a situation where the electrical power is greater than mechanical power. So it will pull it back, right? Pull it back and settle at delta 1. Settle at delta 1. Yeah? So it will oscillate about delta 1 PM1 and it will settle at delta 1. Right? Now how far it swings depends on area 1 and area 2. Area 1 must equal area 2. Yeah? So what we will do at this point, we will take a short break and then we'll come back and we'll relook at this. Yeah? We'll take a short break of 5 minutes and we'll come back and relook at it. Yeah.
Is this the in the synchronous machine generate the flux? Right? Is this delta is the phase difference between the stator and rotor?
Yeah.
So you will use to represent the field flux or flux linkage?
Yeah. Okay, so all right, so this is a situation we have. The electrical power, the equation for electrical power is a sinusoidal curve, which is PE equal to the red color curve, PE equal to P max sine delta, and the green horizontal line is the mechanical power output from the turbine. Yeah. So let's say initially PM0 is the mechanical power output of the turbine. That means this generator must be supplying an electrical load which is equal to PM0. So the operating point is the intersection of the red and the green line, because the electrical power and mechanical power must be the same, right? So it operates at delta naught. Then all of a sudden we increase the mechanical power to PM1. Now if the turbine output is PM1, then the machine must be supplying a greater load. So that means the load has changed. Yeah. So now the machine must be operating at delta 1. Yeah. If it settles, like if it's a stable operating point, like if it has reached a steady state, then it must be delta 1. But we don't know if it's reached there yet. Yeah. But if it has, then delta 1 has to be the point, because that's the intersection of the mechanical power and the electrical power. Okay. Now, say the load changes all of a sudden, the turbine mechanical power output rises from PM0 to PM1, right? So when that happens, my question is, this is my question to you, why doesn't it just go like that and just stop there? That's your question too? That's my question too. Why doesn't it? My question is, like, it was initially here, right? It was initially here. It's a good question, isn't it? The question, like, it's initially here. This now have increased from there to there, because the load must have increased. Yeah. So according to our thinking, it should go, and this is our new operating point. Sure, it must be the new operating point. That's okay. It may be, right? But why doesn't it go from that first point, first blue dotted line, move up slowly, right, and stop at the second dotted line? Why doesn't it do that? Or does it do that, or why doesn't it do that? So, huh? Well, if you are at the first blue dotted line, right, first blue dotted line, which is on the left, one to the left, the mechanical power gone from PM0 to PM1. So all of us, mechanical power has gone up, but your electrical power is still low, right? Is below the mechanical power. So PM minus PE is a positive number. That means on that this differential equation, well, we are looking here on the left hand side of this differential equation is a positive number. So what should happen? That means, well, assume D equal to 0 on the right hand side. So you are talking about an acceleration here. No? Acceleration is positive. So it's accelerating. It's not going to go slowly. It's accelerating. So it's going to shoot past that point, that blue dotted line on the right, on the top. It's going to shoot past that because we are accelerating. And then when it goes above that, what happens? It starts decelerating and then stop. And then it needs to be dragged back, isn't it? It's decelerate and starts accelerating the other way, isn't it? So it will oscillate. So it won't just go and stop here, because it won't go and stop here. It is going to accelerate towards that, shoot past that, get to that, and then come back again, and back again, back again, back again. But it will keep oscillating its same magnitude if this D is 0. If this D is non-zero, then it will damp. It will damp and it will go to 0. Okay? So these sections that I'm talking about is important. Surely there might be a question. I can't remember, but I can't tell you what is in there anyway. But I think you look at in the past exams, there's been questions, right? Sorry, what? Yeah. So if A1 equal to A2, that's fine, right? If A1 equal to A2, it's coming back. But what if A1 equal to A2 is actually something like this? If A1 equal to A2 is something like that, going past that point delta 3. Right? If it's going past delta 3, then it's not going to come back. Yeah, we'll get to that. I mean, yeah, we'll get to that. So we will get to that. So A1 equal to A2, so this delta 2 we can determine, because if you know the area A1, we can determine delta 2 because area 2 must equal area 1. We can determine delta 2, right? So if the mechanical power output is high enough, and if delta 2 passes delta 3, we have a problem, isn't it? Yeah, we have a problem. So when the angle increases from delta 0 to delta 1, it takes time, right? Isn't it? It takes time. So if PM0 is quite high, then that delta 1 will shift more to the right, yeah, more to the right, which will shift delta 2 more to the right, even past delta 3, and we have a problem then. It will not, the angle will not come back to where it should come back to the intersection point, and it's unstable. So that question, why doesn't it slowly go and finish there, is an important question, right? Because it's accelerating, right? So we can now use the equal area criterion to actually determine what is this angle delta 2 is, okay? So look at an example. Don't bother about the proofs and things like that, right? Don't bother about that. So here is the equal area criterion example. Here is the example. The synchronous generator shown in the figure below, which is this guy, same as the example we considered before, is initially operating in steady state, condition given in the previous SMIB example, single machine field bus example. When a temporary 3-phase to ground bolted short circuit occurs on line 1-3 at bus 1. So at bus 1, at this point, on bus 1 there is a short circuit. So this bus voltage becomes 0. Right? That bus voltage becomes 0. Okay? That's what's going to happen. So this is a different condition we are talking about to the one that we looked at before. The one that we looked at before, the mechanical power went from one value to a higher value. Here, mechanical power is remaining the same, the electrical power will disappear. Yeah? Okay, because the bus voltage is going to be 0, so PE is going to be 0, because PE is the bus voltage multiplied by the internal voltage of the generator times some other terms. Okay, so short circuit occurs shown on point F in the figure. 3 cycles later, the fault extinguishes by itself. The system returns to pre-fault condition. So after 3 cycles, the short circuit disappears. Okay, so then electrical power requirement comes back. Determine whether the stability is or is not maintained and determine the maximum power angle. It's called the power angle also, right? Delta is the power angle. The inertia constant of the generating unit is 3 per unit seconds on the system base. Assume PM remains constant throughout the disturbance. So we are asked to assume that PM remains constant throughout the disturbance. So the disturbance is for 3 cycles, the bus 1 is going to be short circuit. Right? When bus 1 short circuit, the electrical power requirement becomes 0. Electrical power output from the generator is 0. So the generator has mechanical power input, but the electrical power output is 0. Right? Then what's going to happen within that period? Because PM minus PE is a positive number. PE is 0. Right? So delta is going to accelerate during that 3 cycles. Right? So this is what we have. So notice the area 1 is different now. So this is PM. Right? So this is where at delta naught is where it's operating. Right? And then a fault occurs. Bus 1 is short circuited. Then electrical power becomes 0. So mechanical power remains the same, right? Electrical power, this curve here drops to that, right? Isn't it? Drops to that. So PM remains the same for 3 cycles. Right? So the area A1 is this guy here. Right? Previous A1 was different. Previous A1 was different. Previous A1 was this guy. Right? So you need to understand the different areas for you to understand this. Okay? So this A1 is now that. So fault is after 3 cycles later, fault is cleared. In other words, the green circle comes back. Okay? Green circle comes back. So what will happen now? When the green circle comes back, your mechanical power is here. Right? Your mechanical power is here at that. Your mechanical power is at that point, right? Electrical power is there, it starts decelerating. Yeah? So angle will still increase but decelerating, and this area A2 must until equal to area A1. Yeah? Will decelerate. Yeah? And then it will be pulled back to the original operating point. So it will come back, it will shoot past, it will oscillate and settle at 1. Because if electrical, it will decelerate and it will come back to that point. Yeah. Because mechanical power we haven't adjusted, so it's the red line. Yeah. So this has accelerated. Right. Right. So originally we are at delta 0, right? And then the short circuit happens at bus 1. So there is no electrical power requirement. So area A1 is as shown, right? Because the electrical power is 0 during that time, is 0 like that. Yeah. So within that time it's going to accelerate, so it's accelerating. Fault is cleared at delta 1, so it starts decelerating during this area A2, right? Yeah, we start decelerating. And then it will come to 0 and then it will pull back to the original operating point. yeah, because PM minus PE is still negative. So the angle has to reduce, so it will oscillate about that original operating point and it will settle at the original operating point. Yeah? Understand? So if you know it's going to be cleared in 3 cycles, right? You know delta naught, you know it's going to create in 3 cycles. So 3 cycles we know how much time it is, because each cycle we know how much time it is. So 3 cycles we know how much time it is. So we know the speed. So omega t plus initial delta naught will be delta 1. Yeah? Okay? So that will be delta 1. So we can then calculate area 1 and therefore we know area 2, so we can calculate delta 2. I'm trying to explain how to calculate so that you can then look at the numbers to the solution to see, to make sense. Right? So delta naught we can calculate, that's no problem, right? Because we know the equation of the sine curve, we know PM is 1, we know, so we can calculate delta naught, that is that calculation, right? And we know the frequency, so we know what 3 cycles is, right? And we know 3 cycles, what 3 cycles mean in seconds, therefore we can calculate delta 1. Delta 1 is that. Right? Because if you know 3 cycles, if you know how much a cycle is, because we know the period, it's 60 hertz, 1 on 60 is the time for 1 cycle, so 3 cycles is 3 times that. So initial angle we know the speed, therefore we can calculate the calculate delta 1, which is that calculation there. There is an equation for delta, for delta. Right? So this is the initial delta naught. This is t squared, and this is related to omega. There must be an equation. This equation here. Yeah, with relating to time. Because if you have the differential equation, from the differential equation, you can actually get. So you have you got this, right? Okay, let's go back to have a look. All right, so you have this equation here. You have during the fault you have this equation, right? This is the swing equation. PM minus PE must equal this equation, swing equation. PE is equal to 0, right? PE is equal to 0. This equation is a swing equation. No friction. Yeah, assume no damping. Assume no damping, right? So this is the swing equation, right? PE equal to 0, right? Okay, and one cycle is 3 cycles is 0.05. 3 times 1 on 60. Yeah, okay. So if you know the second derivative, then you can differentiate once and you get this equation, right? Because you have, if you differentiate with respect to integrate with respect to t, you get PMT. So take this equation, integrate both sides, then you have this t term appearing. You integrate it once more time, delta t on t becomes delta. This t here becomes t squared on 2, right? So that 2 becomes 4, right? T squared on 2 plus delta naught. Yeah? Initial velocity is 0 because it was in steady state. It was in steady state. Initial velocity is 0 because this term here is 0 because initial velocity is 0. Right? So we can compute delta. T is 0.05. Delta 1. So that's delta 1. Right? So then we can compute the area A1. Right? We can compute the area A1, which is that rectangular area, this rectangular area. Because you know delta 1, you know delta naught. You know this is 1. So you can compute the rectangular area. Rectangular area is this much. It's simply the rectangle, area of the rectangle. And then area A2, delta 1 to delta 2, right? Angle is going from delta 1 to delta 2. PE minus PM delta d delta. So this area here, PM minus PE minus PM, right? Which is this, PM minus PE. You integrate with respect to delta, right? Going from delta 1 to delta 2, going from delta 1 to delta 2. PE is this expression there, equation of the sine curve, minus PM is 1. So you obtain, you can do this simple integration, sine becomes cos, these are the cos terms. 1 is just a constant, right? It's simply delta. And then you have this nonlinear equation to solve. And you can use either Gauss-Seidel or Newton-Raphson to find delta, and you can arrive at this equation. Right? But I mean, you're not going to be asked like difficult questions, like solve nonlinear equations and things like that. But you can do Gauss-Seidel anyway. You can try. Because you need to know how to do Gauss-Seidel for power flow anyway, right? Okay. So the maximum angle delta 2 does not exceed 180 minus delta naught. Because, yeah, if it exceeds 180 minus delta naught, you're at the rightmost intersection point on that sine curve with the PM curve, right? So if if delta 3 is less than 180 minus delta naught, then the system is transiently stable. After the disturbance, system can return to back to a stable operating point. Yeah, because delta 3, right, if this point here goes past delta 3, then it's unstable. Delta 3 is essentially 180 minus delta naught. Okay. So you will have to spend a bit of time understanding what I'm just saying. Yeah, it's not hard to understand, but you need to sit and understand. Yeah, it returns to delta naught in steady state. Because that's where the mechanical power and electrical power intersect. Okay. So if we wait long enough to clear the fault, what's going to happen? This delta naught is going to move to the right, isn't it? Yeah. So there is a clearing time. If you don't clear it before that clearing time, it will become unstable because A1 equal to A2 then will go past delta 3. Right? If A1 equal to A2 is such that delta 2 is actually on top of delta 3, then that's the clearing time, that's the threshold. Right? So, all right, so these are some MATLAB simulations. It shows how the system oscillates, because we know it's oscillate about the operating point and settles eventually. So that's without friction. I said without friction. Without friction, it will be oscillating about the operating point back and forward, right? So when there is some friction, when d is not equal to 0, it will operate about the operating point and settles at the operating point. Yeah. So there is something called critical clearing time, which I talked about. So this is delta naught, right? This is the initial stable operating point. This is the critical angle, right? So it's cleared when the angle delta is a critical angle, and critical angle is defined so that A1 is equal to A2, and your A2 is such that it actually reaches this point delta 3. Yeah. Because if you wait any further, this A3, I mean the angle delta 2 will move past delta 3, so that delta will never return back to its original value. Yeah. So at the case that we are looking at here, delta 3 coincides with delta 2. Yeah. And that's, so fault is actually cleared at this point when delta equals delta critical. So A1 and A2 are the same, and delta 2 and delta 3 are the same. Yeah? If you wait any longer to clear it, if delta critical increase beyond that, then to make A1 equal to A2, delta 2 has to be to the right of delta 3. Yeah? And that way delta 2 will never return back to delta 0. Yeah? So there is something called a critical clearing time, because critical angle delta depends on the clearing time. I'm pretty sure there has been questions in the past on, determine the, clearing time and so on. So you need to look at that. There are questions in the tutorial, right? If you understood what I said. So those are two different case scenarios that I looked at. I just take the mechanical power output, I increase the mechanical power output. Yeah, that's one scenario. Second scenario I have looked at now, you have a mechanical power output and then the electrical power output drops all of a sudden. Right? That's the second scenario we looked at. Yeah? Then area A1 is actually a rectangle. In the first scenario, A1 was not a rectangle. So you need to be able to draw these things by yourself without looking. Yeah? And there is a third scenario which I'm going to talk about now. Right? A third scenario. Okay, this is the third scenario. Second example is a third scenario. Right? The third scenario. It's the same system. Instead of a bolted fault at bus bar 1, now the fault is occurring at bus bar 3, in the middle of bus bar 3. Yeah? So this is a different case. So what is happening here? So this is the circuit. Right? This is the circuit. Fault is occurring at this node 3 at that point. That short circuits to ground. Okay? That short circuits to ground. So during the fault, this is how the circuit looks like. See, that middle part is short circuited, is ground. Yeah? So this is before the fault, looks like that. During the fault, this thing connects to ground. During the fault. So the during the fault circuit looks like that, because that middle point connects to ground now. This point here connects to ground. Yeah? So it looks like that, right? Looks like that during the fault. Okay? So during the fault, notice that here, during the fault, previously this went to ground, right? So this voltage dropped to 0 and PE became 0, right? But here, this time PE is not going to be 0 because this is no longer 0. It's 0 here, right? Voltage is 0 there. Yeah? So PE is not going to be 0. So what's going to happen is this. Now, during the fault, right? During the fault, we find the Thevenin equivalent circuit looking that way. What this generator is seeing. Yeah? What the generator sees. So if I look at the Thevenin equivalent circuit to the right, okay? What is the Thevenin impedance? Thevenin impedance is going to be like this, right? So I have this is, let's say, node A, this is B, this is A, right? I have that J.4, okay? And then I have that J.2, right? And I have infinite bus, 1 angle 0, right? And then I have connecting to ground, right? And I have this point connecting to ground. I have something like this, isn't it? Right? I have something like that. So how do I find the Thevenin impedance looking into that? I short circuit this guy, right? And if I short circuit that guy, then what happens? This guy disappears, right? Yeah? So then this and this, well, that's nothing there. This 0.2 is going to be in parallel with this guy, right? In series with this guy. Okay? So this is going to be in parallel with that, in series with that. Yeah? So that's the Thevenin impedance. This guy in parallel with this guy, in series with that guy. Basically, this guy is in parallel with this guy, series with this guy. Is a Thevenin impedance, which is that. Okay? So we can find the Thevenin impedance to be that. What is the Thevenin voltage? Okay, let's have a look. Okay, Thevenin voltage is the voltage that appears across A and B, open circuit voltage. Yeah, so open circuit voltage is the voltage across there to there is still 1 angle 0. Okay, yeah, and voltage across that and that is still 1 angle 0. So it's going to get divided. 1 angle 0 is going to get divided over that and that. Yeah? Which is this guy here. Voltage divider. So that's the Thevenin voltage. Right? It's going to be divided across those two reactances. Because you have 1 angle 0 across there to there. So there to there, voltage is going to get divided. So this voltage appears there at point A. Right? So we have the Thevenin voltage, Thevenin resistance. So now I can connect that above circuit, this circuit here can be represented like that. We know the Thevenin voltage, Thevenin impedance, right? So during the fault, now I can write what is the power injected by the generator, because it is going to be 1.2812 multiplied by the Thevenin voltage sine delta divided by x Thevenin. Right? X Thevenin, right? So I have this. So this is the electrical power equation. Electrical power equation when the fault occurs, during the fault. Electrical power curve looks like that expression during the fault. Okay? So, so what do we have now? This is what we have. This is what we have. After the fault, right? After the fault, what we do is we actually, the question says, after the fault, we remove that line. We remove this line. After the fault, we remove this line. Right? So when you remove the line, you have a different power curve because you have all those impedances connected in series. Yeah? Previously, the reactance connecting the left-hand side and the right-hand side was something because we had a parallel line. Now we don't have a parallel line, it's a different line, right? We have a different power curve. So there are three power curves, right? Before the fault, during the fault, and after the fault. So you can check this, right? Now, before the fault, the power curve looked like that. Before the fault. Okay? During the fault, power curve looks like that. There is an expression there. I mean, you can go through that. It's no point me. I need to explain to you so that you can follow. That's the power curve during the fault. Right? And after the fault, the power curve looks like this. Right? Okay? Now, in all three cases, the circuit looks like this. Okay? This value changes, x value changes. right? And also actually this value changes as well. This value changes as well. I'll say A, right? That value changes as well. A and X changes, but in all three cases, the circuit looks like that. We need to make it look like that. Yeah? Circuit will look like this. It looks like that. Okay? So we have the red color before the fault, green color during the fault, blue color after the fault. Okay? So before the fault, this is the operating point here. Okay? And a fault occurs during the fault. During the fault, your green curve is below the mechanical power curve, which is that, which is in yellow, right? Your green curve is below the yellow curve, right? So delta keeps increasing, right? Delta keeps increasing. It will increase to this value, yeah? And then we clear the fault because we are talking about a critical angle to determine critical angle. So we clear a fault, and then we are looking at the blue curve. It will start decelerating, delta starts decelerating, yeah, rotor starts decelerating, and it will move to this point delta 3 because it's a critical angle that we are talking about. So A1 must equal A2 if we want to determine that critical angle delta critical, right? If you want to determine delta critical, then A1 must equal A2. So instead of me going through it line by line, I think this explanation I'm providing is the most critical for you to understand what I'm saying. Yeah? Do you think so? I mean, if you have difficulty understanding, you are welcome to come and see me, but that's what I just explained there is what is important for you to follow what is in the notes. Right? So this is before the fault, this is during fault, this is after fault. And this is where the fault is cleared. Yeah.
Why would before and after the fault not be the same?
Because we have removed one line, remember? Because after the fault we removed this line. If we don't remove the line, if you put it back, it will be the same thing. You're right. But I removed the line. Because before the fault, X is this X, right?
Yes.
After the fault, I have removed this line. So it's X has changed.
So you clear the fault is removed.
Yeah, exactly.
You don't restore the line.
No, you didn't in this situation, we didn't restore the line, we removed the line. Because this was a parallel line.
Why would you not restore it?
Well, for some reason, let's say you can't. I mean, there are some cases you can restore it, some cases you can't. This is just an example, just saying we can't restore it. Yeah, that's why we have three different curves. Yeah, in all cases, right, before, during, and after, you always write the circuit like this, right? It's important, like the highlighted yellow. You're always writing like that. That X changes for the three cases and A changes. Yeah.
where we have the electrical power burn at 0.
Which one?
Slide 56, I think.
Slide 56. Yeah. We restored it.
You restore it.
Yeah.
How do we know when we restore it?
I mean, you have to be told.
Okay. Because here the fault.
Yeah, we restored the line here. Because sometimes you can restore it, sometimes you don't restore it. Like you have to know. I mean, what happens afterward depends on whether you restore it or not. Make sense? Good. Okay. So that's so you have an understanding. So if you don't restore, if you don't clear the faults before a critical angle delta, right? System will not return to a stable operating point. That's what that curve is trying to say. If delta is less than critical, delta critical, system will return to a stable operating point, transiently stable. If it doesn't, then delta will keep increasing because it's gone past that point delta 3 and it won't return. Right? So now I want to move to section 7.3, generator 2-axis model. Analysis of more detailed synchronous machine models require that each machine model be expressed in a form of reference that rotates at the same speed as its rotor. The standard approach is to use DQ reference frame in which the major direct axis D is aligned with the rotor poles and quadrature Q axis leads to direct axis by 90 degrees. So here we have a direct axis and a quadrature axis. So to simplify, right? Okay, you have an electric circuit. Electric circuit will have a certain reference where you take as angle 0, right? Yeah? And so we have a real axis and imaginary axis because when you take as reference 0 and we have another voltage, let's say at angle not equal to 0, right? So that voltage will have a real part and an imaginary part. Yeah? So that's what you see, the real and imaginary, right? So that's a frame of reference where I have drawn the real axis and imaginary axis, frame of reference, and that frame of reference actually rotates at angle at speed omega because we are representing omega t plus a phase angle, and that phase angle is what we represent as a phasor. Yeah? So you have the imaginary and real which is rotating at angular frequency omega, right? We can also think about another reference frame, let's call it the DQ frame, right? And the where the it's a DQ frame and the other reference frame where I define the real and the imaginary, they are both rotating at some angle omega. So the only difference between the two is that there is a angular displacement delta between the two, right? So if I have a vector in the imaginary and real reference frame, I want it in the DQ reference frame, all I have to do is like change the angle by 90 minus theta, right? Change the angle by 90 minus theta. So in other words, we need to rotate the vector. If we are going from one reference frame to another reference frame, I need to rotate the vector by 90 minus theta. So in other words, if I have VR and VI, real part and imaginary part of some vector, and I want to get the dq values in the dq reference frame, I need to rotate by an angle 90 minus delta, which will be that matrix operation, right? Because that matrix operation is a rotation operation. Multiplied by VR VI will give me dq. Then if I have dq values and if I want to know the VR and VI values, well, it's the inverse of that matrix I need to multiply by, pre-multiply by, right? So it's between the two reference frames, it's only an angle difference of delta. And if I go back and show you the two reference frames, the q is leading the real axis by an angle delta. And we know what delta is, right? Delta is that power angle of the voltage E, internal voltage E. So, we can then, like, you know, your voltage vector E, right? Internal voltage of the generator, well, it's E angle theta, right? It has a real part and an imaginary part. So it's in the, if I can say, it is the RI reference frame, let's say, RI reference frame, right? So I have ER and EI. I can convert ER and EI into EQ and ED, into the DQ reference frame. I can convert that value, right? So in the IR reference frame, I can write the equation, right? Those equations in the DQ reference frame, because you can separate the real parts and the imaginary parts, it will just turn out to be those. If does the formula sheet actually provides those equations? No? Okay. So if it just turns into those equations, because if I write in the IR reference frame, because E has an angle delta, so it has a real part and an imaginary part, right? So we can separate the imaginary parts and the real parts. That the voltage E in the IR reference frame, I can convert that to the DQ reference frame. Again, it will have a D component and a Q component. I can separate them out because they are orthogonal, right? I can say the D part is this and the Q part is that. And that's what we see, what we've written there, right? Where VD and VJQ and ID and IJQ are the generator's terminal voltage and current shifted into the generator's reference frame, because DQ is a generator reference frame. And EFD is proportional to the field voltage, right? Okay. So I think we have done quite a bit today. So maybe we'll leave that at this point, right? We'll leave it at this point, and I'll come back and start this lecture in the next week, right? Because we've gone the whole time now. We'll stop it there and we'll come back to it.